The last three sections we'll be talking about hybrid orbitals. So hybrid orbitals are referring to a mixture of orbitals. So before we talked about the s, p, d, and f orbitals, and I mentioned in this class we'll focus mainly on the s and p. Well, now I'm going to tell you about the hybrid orbitals formed from s and p orbitals. So if we look at methane, which is carbon attached to 4 hydrogens, it is what is called sp3 hybridized. The carbon is sp3 hybridized. What that means is that the carbon is using sp3 hybrid orbitals to form bonds with the hydrogen atoms. What is an sp3 hybrid orbital? It's an orbital that's made from mixing one s orbital and 3 p orbitals. So you take the 2s orbital for carbon and all 3 of the 2p orbitals, mix them together, and out you get 4 hybrid orbitals. So the number of orbitals in has to always equal the number of hybrid orbitals out. And this is what the sp3 orbital looks like in a cartoon. Notice that this lobe over here is bigger than this little guy here. And that's helpful because this part of the lobe is going to be used in bonding, and that allows for a better overlap with the orbitals that it will bond with. And notice the notation sp3. The superscript 3 means we took 3 p orbitals, all 3 of the p orbitals, mixed it with the 1 2s orbital to get out 4 sp3 orbitals. And the idea of hybridization was proposed by a chemist named Linus Pauling to explain the observed molecular geometry. Because if we were sticking with these unhybridized orbitals, the geometry would not match what was experimentally found. Here's another representation. So the sp3 orbitals in a carbon atom overlap with the 1s orbitals of an H atom. So this is a 1s orbital, and then there's an sp3 orbital from the carbon overlapping with that. So we could think of this carbon having 4 sp3 orbitals, and each of those hydrogens just have a 1s orbital. And then each CH bond has a strength of 439 kilojoules per mole and a length of 109 picometers. The bond angle, which is defined by this angle, it's defined with 3 atoms in a plane, is 109.5. Let's look at sp3 orbitals and the structure of ethane. So ethane is C2H6. It's an organic compound with 2 carbons and 6 hydrogens. Here are some representations of ethane. This is the one we're going to focus on, the bond line structure. So in this, you have 2 carbons bonded to each other, and that's going to form a sigma bond. A sigma bond is formed between those 2 carbons by each of their sp3 orbitals overlapping. So each carbon has an sp3 orbital overlapping with the other carbon. And remember, with the sp3 orbitals, we have 4 of them available. So that means that this carbon has 4 sp3 orbitals, as does this carbon. And these drawings start to get a little bit confusing, I know. Let me actually use a different color for the carbons. So each of those carbons has 4 sp3 hybrid orbitals. The 2 carbons bond with each other by overlapping an sp3 orbital from each. And when we do that, we form a covalent bond that we call a sigma bond. And the sigma bond is a cylindrically symmetrical type of bond. All plain single bonds are sigma bonds. Now we also have hydrogen atoms here. Hydrogen atoms just have a 1s orbital. There are no p orbitals available to it to do any type of hybridization, so hydrogens don't undergo hybridization. So they're just going to have their 1s orbital overlapping with the sp3 orbital. And that's how you get to the bonding. So the carbon would be, both carbons would be sp3 hybridized. The carbon-carbon bond has a strength of 377 kilojoules per mole. And the bond angles, all the bond angles here would be 109. So here's a picture of what I was talking about. Here we have the overlapping sp3 orbitals. Here you have the two sp3 hybridized carbon coming together to form that bond. And then you also have hydrogens. It's not showing the hydrogens. They're going to come in here and bond also with those sp3 orbitals. Now here is an example. Draw a bond line structure for propane. The formula is given. And predict the value of each bond angle and indicate the overall shape of the molecule. Here's the solution. So this is the bond line structure. So every carbon has 4 bonds to it. And they're all single bonds. There are no double or triple bonds in this. And each carbon is going to be sp3 hybridized. And the hydrogens, again, don't have a hybridization. The geometry, if you're sp3 hybridized, the geometry around that atom is called tetrahedral, which means all of the corresponding bond angles are 109 degrees approximately. And this is the shape of the molecule here. If you have your model kit, you could actually try and assemble the molecule and look at it and see if it matches this drawing. Okay, the next topic would be sp2 orbitals. So again, a hybrid orbital, but instead of taking 3 p orbitals and mixing them with an s orbital, we're taking 2 of the p orbitals. That will mean that we'll get 3 sp2 orbitals out, because the number of orbitals in equal the number of hybrid orbitals out. So if we mix an s orbital plus 2 p orbitals, we're going to get out 3 sp2 orbitals. That means we have left over an unhybridized p orbital. So the sp2 orbitals are going to all be in the same plane at an angle of 120 degrees away from each other. So in green, the lobes in green, these represent the sp2 orbitals. They're 120 degrees apart. Then perpendicular to that, you have the remaining unhybridized p orbital. And then this is just a different view looking down from the top of the red lobe of the unhybridized p orbital. So if we look at the molecule called ethylene, which is 2 carbons double bonded to each other, has a formula of C2H4. Those carbons are going to be sp2 hybridized, meaning that each one has 3 sp2 hybrid orbitals. The sp2 hybrid orbitals will overlap to form sigma bonds. So the carbon-carbon sigma bond is formed by the overlap of each carbon's sp2 orbitals. The carbon-hydrogen bonds are formed by overlapping of the carbon sp2 hybrid orbital and the hydrogen 1s orbital. And then what about that second bond in the double bond? So that second bond is called a pi bond. So single bonds are sigma bonds. The second bond, the double bond, is called a pi bond because a double bond has 2 bonds in it, right? It has the sigma bond and the pi bond. A pi bond is formed by overlapping unhybridized p orbitals. So this is a representation of the pi bond. So whenever you see a carbon in a double bond, it's going to be sp2 hybridized. So the hydrogen atoms form sigma bonds with the sp2 orbitals, and then the bond angles are about 120 degrees. So remember, if something's sp2 hybridized, the bond angles around that atom will be 120 degrees. And then the carbon-carbon double bond is shorter and stronger than the corresponding single bond in ethane. So the thing to remember here is a double bond is made up of one sigma bond and one pi bond. And the pi bond is formed by the overlap of unhybridized p orbital, where the sigma bond uses the hybrid sp2 orbitals. So let's look at an example. You may want to pause the video and try this. What is the hybridization of carbon and formaldehyde shown here? What's the hybridization of oxygen? What's the hybridization of the hydrogens? So here's the solution. Let's start with the easy one, hydrogen. Well, they're never hybridized, so there isn't a hybridization. They just have an unhybridized s orbital. For the carbon, notice it's double bonded, so it's going to be sp2. So that means it has an sp2 orbital overlapping with the hydrogen s orbital to form the carbon-hydrogen bond there. Then this hydrogen s orbital is overlapping with the second carbon sp2 orbital to form that carbon-hydrogen bond. And then we have the bonds with oxygen. It's a double bond, which means it has a sigma bond plus a pi bond. So the sigma bond portion of the double bond is formed by overlapping that third and final sp2 orbital with an orbital from oxygen. And then the double bond, the pi bond, uses the unhybridized p orbital on carbon to overlap with oxygen. So oxygen's also double bonded, so it's going to be sp2 hybridized. So for the oxygen, it will have an sp2 orbital with a lone pair there in it, an sp2 orbital with a second lone pair, and then the third sp2 orbital will be overlapping with an sp2 orbital of carbon to form the sigma bond. And then finally, its unhybridized p orbital will overlap with the carbon unhybridized p orbital to form the pi bond. So this quickly gets kind of complex, but we will do a lot of examples of this on Wednesday. The final topic is sp orbitals and the structure of acetylene. Acetylene has this formula. So carbon can form a triple bond by sharing 6 electrons. And to do this, it forms 2 sp hybrid orbitals. So where the sp2 was formed from an s orbital and 2 p orbitals, the sp hybrid orbital is formed from 1 s orbital and 1 p orbital, which means that you have 2 unhybridized p orbitals left over, and those 2 unhybridized p orbitals are available to form pi bonds. And a triple bond would have 1 sigma bond and 2 pi bonds. Now, whenever you have an sp hybridized atom, the sp orbitals are going to be oriented 180 degrees apart from each other. And then the p orbitals will be perpendicular to those, along the y and z axis, to those sp orbitals. And again, these pictures get a little bit confusing to understand. But if we take each carbon that's sp hybridized, the lobes in green are the sp orbitals, right here. And then the lobes in red and blue are the unhybridized p orbitals. So when you have this overlap here, you form the sigma bond of acetylene. So this is the bond line structure of acetylene. So one of those 3 bonds is a sigma bond, and that's formed by this overlap here. The other 2 bonds in the triple bond are both pi bonds, and those are formed from the overlap of the p orbitals here. And then finally, these carbon-hydrogen bonds are formed from an overlap of the other sp orbitals with the hydrogen 1s orbital, and the hydrogen is not shown in that picture. So as a result, you have a sharing of 6 electrons using 2 sp orbitals to form sigma bonds with hydrogens, and here you now get the shortest and strongest carbon-carbon bond. Here is a comparison of the bond strengths and bond lengths in a variety of compounds. Notice here that the triple bond is stronger and shorter than the double bond, which is stronger and shorter than the single carbon-carbon bond. And also the carbon-hydrogen bond with an sp3 hybridized carbon is not as strong as the carbon-hydrogen bond with an sp2, which is not as strong as the carbon-hydrogen bond with an sp hybridized carbon. So let's do one final example. Draw the bond line structure for propyne, and then indicate the hybridization of each carbon and the orbitals on each carbon, predict a value for the bond angle. So notice you've got a carbon-carbon triple bond. So if we draw the bond line structure, it looks like this. So here we've got 2 carbons in a triple bond, and then we've got another carbon which is singly bonded to all of the atoms around it. So the carbon that just has single bonds is sp3 hybridized. The carbons that are triply bonded are sp hybridized. And with the exception of something called allenes, you can just remember sp3 carbons just have single bonds, sp2 carbons have double bonds, and sp carbons have triple bonds. Now for the carbon-hydrogen bonds here, those are formed by an overlap of an sp3 orbital on that carbon and the hydrogen 1s orbital. For this carbon-hydrogen bond, you have the hydrogen 1s orbital overlapping with the sp orbital. For this carbon-carbon bond, you have a carbon sp3 orbital overlapping with a carbon sp. And then for the carbon-carbon triple bond, well, there's 3 bonds in a triple bond. One of those bonds is the sigma bond. That's formed by the overlap of the sp hybrid orbitals. And the other 2 bonds are pi bonds, which are formed by the overlap of unhybridized p orbitals. Now the bond angle between the 3 carbon atoms is 180 degrees. The bond angle between this carbon, and the hydrogen is 180. And then the bond angle here would be 109. The bond angle here would be 109. Okay, that's it for your first lecture. The next steps are to read the assigned sections from the book if you haven't already done so, and then come to class with your questions ready. We will be doing problems. Probably the hardest material from this to grasp is all of the hybridization material. So we will work on that a lot on Wednesday.